Good afternoon. Today is the second presentation of Professor Sergei Kuznetsov from Faculty of Computer Science of the University of Higher Study of Economics. And the title of the second presentation is Explainable Knowledge Discovery with Interval Pattern Structure. So again, Sergei, thank you very much to be with us, and thank you for spending your time with us.
Thank you very much, Francisco, for this nice introduction. Thank you for the kind invitation, and I'm happy and honored to be here and give a talk. My name is hard to pronounce, but it's the most frequent name in the world, like Ferreiro. But I like more Ferrari, but more than Smith and Schmidt. Ferrari sounds really chic. Okay, this is a joint talk with my student, Ananta Mat, from Syria. He's studying at Moscow University, and we made this. We made together this work, and I will also switch to some other slides because I would show you several works where interval pattern structures are applied. And here the motivation was to increase interpretability, explainability of our analysis. It's often needed in many domains, especially in medicine, in banking, credit scoring, engineering of complex systems. There's recent stories with Boeing show that if you don't understand an AI system, it may cost a lot, including human lives. So, for example, no doctor would trust completely a black box that would recommend him doing something before he sees or she sees the real reasons for an explanation why he or she need to proceed in a certain way. So here we propose some views based on our approaches to local interpretability, feature importance, and counterfactual explanation, which is important tools of explainable AI, and I would make respective definitions on the way. So, but first we recall the basic construction I introduced you yesterday for binary data, where we have the starting point is the simplest type of data, binary data, given by object attribute matrices called contexts. Rows stay for objects, columns for attributes, and these two important operators, they are denoted by one symbol prime with a slight abuse of notation. For a subset of objects A prime is a set of all common attributes of these objects, and for a subset of attributes B prime is the set of all objects sharing all attributes from B. And with the use of these operators, we get the basic tool of this approach, which is called a formal concept. It's a pair AB, where A is a set of objects, B is a set of attributes, and A prime equals B, B prime equals A. In binary matrix, you can see it as a submatrix filled with ones, which is maximal with respect to inclusion, with respect to this property. If you try to extend it, we get zeros in a row or in a column. The four concepts are partially ordered, like concepts in science and methodology. For example, if we consider the concept of mammalia and vertebrata, then vertebrata would be more general class than mammalia, because all mammalia are vertebrata, but as for their properties, there's reverse containment. All the properties of the turbulator are properties of mammalian. And this definition of a concept, as I showed yesterday, follow the accidental tradition of understanding what is a concept, which starts at least from Logique de Port-Royal and have roots in the Aristotle's ideas. But here we'll consider the extension of this model called pattern structures, where instead of set of attributes, we have a meet semi-lattice on the set of all possible object descriptions. Meet is another word for infimum or intersection, if you want, and it means that it is an idempotent, commutative, and associative operation, which we interpret as similarity operation. It takes two descriptions of two objects to a maximal common description, actually. And here delta is a mapping that takes every object to its description. Then this triple G D delta is called a pattern structure, with the condition that the set delta of G makes a complete subsemi-lattice. It's a technical requirement. Complete means that it is defined for any set of descriptions, including the empty set and the finite set, infinite sets, if they occur. So then the derivative operators, derivation operators, or polarities, if we recall the term of Garrett-Birkhoff, are defined as follows. For a subset of objects A diamond is the intersimilarity of all object descriptions from objects from the set A. Now, similarity in terms of this intersection, meet, or infimum, whatever you call it. And for a description D diamond is the set of all objects such that they match this description D. So sort of contain this description D in terms of this relation. I cannot show. In terms of this relation, which is called a natural order of the semi-lattice. It is defined in this way. Like a standard set theoretic containment can be defined through via intersection. Then again, a pair AD is called a pattern concept if A diamond is D and D diamond is A. And we can define in a similar way the tools we have in a binary representation. For example, we can define an implication on descriptions, which means D1 implies D2. If all objects matching D1 with their descriptions also match descriptions of D2. And in the same way, we generalize the notion of association rule. Here, it's also D1 implies D2 with confidence as a C and support S. If the confidence is equal actually to the ratio of objects both matching D1 and D2 over the number of objects matching D1. And support has the same nominator and denominator the number of all objects. Let's follow the standard definitions in data mining, but for arbitrary descriptions. Here, yesterday we considered several examples of pattern structures, including those based on descriptions given by sets of labeled graphs with labeled vertices and edges. And today I would like to dwell more on interval pattern structures where descriptions are intervals, or more exact, tuples of intervals. The definition of intersection is very simple, but may first seem unintuitive, because intersection of two intervals is defined as the actually convex hull of this of these two intervals, the minimal interval that contain both, which maybe you would like to call a union, but we still keep to the uniformity of our terminology and call it intersection, and you can understand it as, for example, in the sense of uncertainty, that if we have uncertainty both described by one interval and another interval, then when you both uncertainties, you need to unite them. In this sense, intersection of descriptions given by attributes, when you take intersection, you get a smaller description. And here, when we compute intersection in this way, we get actually less information. Larger interval means less information, more uncertainty. And then the relation is defined, the subsumption relation is defined in the same way. So following the general definition in the line above, it is defined as the fact that E is subsumed by F if actually E is larger than F. It contains it as an interval. E is larger than interval F. Again, the intuition is that uncertainty is E is more uncertain. So if this is here, then we come to an example of a toy data set with just 3 objects and 2 numerical attributes. We have then all possible intersection of interval tuples. Here we have the original data, object 1, object 2, object 3. Here's intersection of the first and second line, and here's the intersection of the second and third line, and here is the intersection of all of them. And if you see, if you want to, there is no intersection just of 1 and 3, because it would contain the description of 2. So that's why we have the intersection of 1 and 3 contains the description of object 2. That's why we need to include a second object in the extent of the concept defined by this description, 1, 5 to 6. And below you see examples of a pattern implication. If something is described by the first attribute values 2 and 4, and doesn't matter what is the value for the second attribute, then actually it should have description 3 and 4. 3 for the first element of the tuple, and 4th for the second. So strictly speaking, I should have written 3, 3, 4, 4. And then an example of a pattern association rule. If we have a tuple 1, 6, 1, 7 for the first and second attribute values, then with certainty 2 over 3, we have 1, 3, 2, 4. These are just examples, and yesterday I showed that a concise representation of all association rules is given actually by the diagram, which is above. So you can express or derive any association rule from association rules attached to the edges of this diagram by composing them. So these are the basic tools, and now we would like to make KNN. The goal here is to make KNN style of reasoning more interpretable. To this end, we introduce this notation, the set of k nearest objects to the one which is classified, denoted by g tau. Then the g KNN diamond denotes the similarity of the k nearest objects to g tau, and it is defined in our terms as intersection of intervals. Then the double diamond means the set of all objects that can be explained by this similarity. We call it closure of the initial set of objects, which is given here. Then we would classify an object in the way depending on the similarity measures, which are quite naturally defined here. This is the distance between two objects within the classified objects and objects in the positive class, and these are distances of the classified object from examples of the negative class. And here is an example, a data set with two numerical features, and we consider KNN for k equals 5. Then the KNN voters will be k nearest objects with respect to Euclidean metric. And our interval pattern structure KNN voters will be objects described by the similarity of the k nearest objects. This is given by this rectangle here, which is corresponds to the tuple of two intervals. It's needless to say that we can see these tuples of intervals as n-dimensional parallelepipeds or hyperrectangles in n-dimensional space, where edges and faces of these parallelepipeds are aligned with axes and faces made by the axis. So here green correspond to positive examples, red to negative examples, and this gray is the query object which is to be classified. And here we see that the similarity with positive examples is higher, 2.45 versus 1.8 to negative examples, so we classified positively. And we also produce what we call explaining hyperrectangle. The similarity of a subset of supporters together with the query object leading to the positive score. And here it is this rectangle. It's only 2 dimensions, it's just a rectangle, no hyperrectangle. And the reason for classification is a hyperrectangle with the similarity of the minimum number of supporters leading to a positive score, together with the query object. That's one. So, as an example, we consider one data set with local interpretability and feature importance classifiers for real. And consider the attributes given in the rows. These attributes related to the acidity, residual sugar, chlorides, free sulfur dioxide, total sulfur dioxide, density, pH, sulfates, and alcohol. And here are ranges. Here are the values of attributes for the object to be classified, particular wine. And here are ranges of feature values. And so the reason classification is given by these intervals. And according to feature importance, based on the information gain entropy reasoning, the reduced reason for classification is given by these intervals. So we can say that actually a wine to be good should be not acid, should contain not much chlorides, and the density should be good, and alcohol should be just average, I would say, lower than the average in this region. So it's quite interpretable to understand what is required for a wine to be good. And here is another branch of this work. It's related to counterfactual explanations. This is another tool of explainable AI, which is based on counterfactuals, which is understood as minimal change in your data that would change its classification. So suppose we have some query, some particular wine, and it is classified as good, but if we change slightly its properties, that it would have been classified as bad. So these minimal changes are often quite intuitive to people, both experts, non-experts, to understand why it was classified in this way. Because with certain changes, small changes, it would be classified differently. So the changes are important, and these features which were changed are important. So to solve this finding minimal changes, we need to solve a mixed integer programming problem, which is not very easy. And then we find these counterfactuals as the nearest objects to the of the opposite class. Look here. The explanation is below. A counterfactual explanation sounds as follows. The wine that was classified as good would have been classified as bad if the values of fixed and volatile acidity, here the largest absolute value, as well as sugar, were larger, and the values of citric acid, sugar, and alcohol were less. So we see here how the changes are important by based on the absolute value of these indications. And we again obtained the minimal explanation as residual sugar in this range, chlorides in this range, and so on. And we are sure that this explanation more intuitive than KNN explanation, where where the Euclidean distance is used, because it merges all attributes in one condition about the neighborhood, and it can be not very clear. An eager approach treats each known object as a query object and classifies it using IPS internal pattern structures based on KNN decisions. If something is correctly classified, then we store it as a its minimal explanation path as a hyperrectangle. Else we ignore it. Yeah, that's. So we made experiments with several data sets: breast cancer, rice, connectionist bench, Parkinson's, spam base, magic gamma telescope from UCI. And here the versions of our approach are here on the left side, and here are baseline approaches like KNN, naive bias, logistic regression, SVM decision trees, random forest, and XGBoost. And you see that the approach, our approaches behave relatively good, sometimes even in the best way. But what matters for us is the actually classifier size. You see that they are drastically smaller than those of other classifiers, with maybe exception of decision trees. Decision trees are known to be quite concise and easily computed, but they have their own drawbacks because they perform local optimization. They are usually quite biased. And I would show you a small example that would, I hope, justify my view on that. And here also the experimental results showing that counterfactual explanation size is also quite nice. And sometimes it can be very short, like this. The wine that was classified as good would have been classified as bad if the value for citric acid was a bit less. In this case, we found an example that was just this amount less and was classified differently. As for my argument about biasness of decision trees, yesterday we had a sort of discussion on this. Recall the example yesterday where we have a data set with fruits, 4 fruits and 3 non-fruits, with fruit being a target attribute, and the other attributes refer to color: white, yellow, green, blue, firmness, firm, non-firm, smooth, non-smooth, round, non-round. And this lattice, concept lattice, gives you all similarities of positive examples, such that some of them can be considered as good classifiers. They are actually generalizations of positive descriptions that do not match negative descriptions. So here we have the full variety, and if we treat this data with decision trees, then we see that we can have based on the standard approaches with entropy information gain, we can obtain 3 trees, and they reflect different aspects of data. The first chosen attribute was color in all the cases, but then one goes for firmness, second for smoothness, and the third for form. And if you take any of this, then they would be blind to the attributes of the second level if new objects arrive. So, to my mind, this is a clear indication that decision trees are biased, and that's also justified by the creation of random forests and XGBoost and similar approaches that would compensate for this biasness in a stochastic way. But we propose first considering non-stochastic global optimization, which is really given by these structures, as concept lattices, where you can have all possible classifiers based on your data. So of course this not very easily scalable, but for some, not all data are big, and for small data we don't need to apply approaches designed for big data. We'd rather consider the whole bunch of possibilities. So, having said this, I go back to my slide here, and I would speak also about another model of data analysis, which is called bicluster, and of similar values. If you have a numerical data set, then the bicluster of theta similar values will be a submatrix such that all entries of this submatrix differ not more than in theta, and all other rows and columns contain values that differ at least in theta. Yeah? So this is again the idea of maximal containment. These subtables are maximal with this property that their difference between entries is no more than theta. Here we see on the left hand side a small data table with 2 highlighted biclusters of similar values. They intersect. They have one common entry with the value 3, but we cannot unite them if we stay for the this choice of parameter theta equal to 1. And interestingly, that we can reduce mining biclusters of this type to finding n-dimensional formal concepts in the following way. We turn our 2-dimensional data into 3-dimensional data with the third axis being reserved for the scale. The scale corresponds to the ordinal attributes, which have the following form: minus I and less or equal than I and more or equal than I, where I is I is a number from 1 to 8. Here we don't need more. If we have just natural numbers from 1 to 8 in the matrix, so it's less or equal than 1, less or equal than 2, less or equal than 3, and so to the 8, and then larger or equal than 1, larger than equal 8, and then it's can be proven that any bicluster of similar values will be a triadic concept. So three-dimensional rectangle, or just parallelepiped, with axes and faces parallel to the axes and faces of the Euclidean space. Yeah, so we can apply our standard algorithms to find them, and as a byproduct we can get dependencies like implications and association rules of the form: if this attribute belongs to this range and this attribute B belongs to this range, then two other attributes belong to these respective ranges. And also with standard tools that are used for computing in two-dimensional and three-dimensional formal concepts. That is another mark. So the conclusion here are quite obvious. We proposed small and simple classifiers and interpretability through reduced reason for classification, which is given by a tuple of intervals, feature importance scores that are computed based on an entropy function, and counterfactual explanation. So we have several variations of this model, which proved to be provide quite interpretable results, which are usually much smaller than baseline classifiers, maybe excluding decision trees, but as I tried to argue, decision trees are biased, so we hope that we propose less biased solutions. Then I will switch to recent work which we suggested, which we reported quite recently in the European Conference on Artificial Intelligence, at the workshop for what FCA can do for AI in Santiago de Compostela, Spain. And it goes about clustering with stable pattern concepts, where we applied our idea of stability, which I mentioned yesterday, and I would like to describe in more detail today. So the motivating example was based on the map of Spain, because we were presenting in Spain. We considered a data set of world cities and select more than 700 cities in the continental Spain with 3 dimensions: longitude, latitude, and size of population. And then we have get the first clustering proposed by K-means from scikit-learn on top of min-max scale data. Looks as follows. The clustering turned out to be purely geographical and gives no regard to the population. So if we change the normalization to make population important, then we obtain the following clustering. That can be interpreted as follows. Purple cluster, big cities, mainly Madrid and around. Not quite a proper interpretation, I would say. Green cluster, cities from in the east. Orange cluster, cities in the northwest. And blue cluster, cities of the south. And here is population means. the clustering seems reasonable on a big scale, but it raises questions when we look at each city in detail. For example, why Jerez de la Frontera is clustered blue? Here it is on the Atlantic coast. So to propose a better clustering, we use our intervals. Yes, again, recalling what are interval pattern structures. The basic approach, which is it is relied on, is formal concept analysis on binary data. It's an example of binary data. Here we can compare the descriptions of two objects using Jacquard similarity coefficient. Just the amount of common attributes over the set of all attributes. A simple way to estimate the similarity is to see how many attributes they have in common. In this work, we are based on interval pattern structures, which, as I said, is an extension of formal concept analysis to numerical data. And our pipeline here was initializing pattern structure, enumerating clusters, and then choosing the best clustering. You know this figure already, and this is again recalling how interval pattern structures look like. Yeah, and you see that, for example, standard formal context can be understood as a pattern structure as well, where descriptions make the power set of the set of all of all attributes. Yes, an example here is our way to discretize data. Reduction of the description space, of course, makes it faster for the computation, but also increases the stability of concepts. What is the stability? Let us see. Delta stability is the difference between support of a pattern and maximal support of the neighboring pattern. So it means that it shows how many objects you should take off from your data set to obtain another pattern. So, for example, here support of this pattern is 30 objects, and delta stability is 20, because you need to extract 20 objects to obtain this one. This measure is easily computed, and moreover, it is has a nice property of being monotonic with respect to data projections. When we add attributes one by one, then there appear stable patterns, but with adding objects, adding attributes, these patterns can become just less stable than they were before. So if we select a threshold, minimal threshold for stability, then we can compute up to this threshold and ignore whatever is below. So this is a nice monotonicity or anti-monotonicity property, can be named differently, which allows you not to compute all patterns and then select the best one, in this case stable one, but select only, compute only which are stable with respect to a certain threshold. And Actually, here we used the previous approaches based on rare descriptions. I wouldn't go into big detail and just show that using this approach based on stability, we computed rectangular clusters from most stable interval tuples. And here are examples of them. Here's a best clustering of 4 clusters with no overlap. Blue cluster, which stay for southern small cities with this constraint for this latitude and population. Orange cluster gives us northern small cities with higher latitude than 39.5 and population less than 16,000. And purple cluster gives you western big cities. And green cluster gives you eastern big cities. Yeah, but if we allow for some overlap, then we actually obtain more interesting picture. This blue cluster is big cities on the northwest with these constraints. Orange cluster, big cities of the southeast, and green cluster is just small cities with a low population. In Pays de Basque, here, I don't know how this region is called, like close to Cadiz and Seville. And purple cluster is Catalonia and Mallorca, which Catalonia is considered as a part of Catalonia as well. So the current clustering has overlaps shown with red crosses and doesn't cover all cities. So we think that it's the task of analysts that use these tools to resolve such a problem. Because we propose a variety of views, and it's actually up to the user to select the best view you would like to take. Yeah, but it's not that we don't claim that this is totally a success story, because we have problems with clustering non-trivial data, like those of famous half moons. If we applied our interval based approach, we get something like that, which is not really expected. But this is also the problem with k-means, and this problem is better solved by approaches which use density-based scan, and its successor optics. And but we are sure that clusters of this form were there are many situations where our approach is better, like here. Yeah. As for running time, we have also described it in this table. It's clustering takes some time, and it's our challenge to make it faster. But to come to the conclusion here, we recall that the pipeline consists of 4 steps. First, we generate interval and Cartesian pattern structures. Cartesian meaning the Cartesian product of different intervals. You can describe it as a tuple. We find a set of stable cluster candidates such that the meaning, so to say, of the cluster remains if we even delete several observations. We enumerate the set of minimal broad non-overlapping clustering, and we select the best clustering candidates based on a set of interestingness measures. And this approach gives some reasonable clustering while running in a matter of seconds. So far about this, and then finally I would show you introduce you another work where we followed was published in this best journal on data mining, where we used interval pattern structures together with a minimal description length to produce a most concise representation of data. This is technically very complicated work. We had to make several revisions before we accepted. But the main idea of compressing data here is that we should define some dictionary denoted by calligraphic H here, so that the total length of description would consist of describing the dictionary, L of H, and describing your data in terms of this dictionary. That, in a sense, would remind you a definition of logarithm of the definition of conditional probability. Yeah, but it's indeed it has a relation to it, since the length of description is inverse to probability in terms of Kolmogorov complexity. And here we applied our interval pattern structures. You see that these definitions of the size of the dictionary, and as an input set we have this numerical data, and our output was the set of hyperrectangles that is the smallest one with respect to the definition I gave before. So it has the sum of its description together with this description of all points given this alphabet is the smallest. So we proposed an algorithm that computes this best intervals and compared them, the algorithm which is called MINT, to baseline approaches, real, crimp, slim, and compared on many data sets. And here we show that it is the fastest one, this green, and returns less patterns that several baseline approaches. It returns more patterns than real crimp, but the diversity of our output is higher. So this is another evaluation metric which shows that it's sort of Pareto optimum. We give more patterns, but with higher diversity. So these are examples of our clustering. You see, is much more interpretable than here, where they just partition the data with vertical and horizontal lines. There's our main competitors, Real Crimp and IPD plus. Yeah, for synthetic patterns it also works not bad. And so here we propose the formalization of numerical patterns based on minimal description length principle that ensures interpretability of patterns, because they are given as tuples of intervals, which are very transparent. They give precise pattern descriptions, and they are non-redundant, and propose high diversity, and the approach is quite scalable as compared to the runtimes of other algorithms. So this work also shows that interval pattern structures is a good tool for data analysis in terms of finding best patterns based on the minimal description lengths. So I'm almost done. Yeah, I think that would be the conclusion. So to conclude, I would say that we considered interval pattern structures as generalization of formal contexts and Galois connections on them. Close descriptions have the form of tuples of intervals. In our case, they can be geometrically seen as hyperrectangles of in n-dimensional space, where faces and edges are aligned with axes and faces of the coordinate system. We showed that biclusters of similar values, important tool of data mining, can be reduced to formal concepts. We showed that interval pattern structures can help interpret results of baseline approaches like KNN and nearest and k-means. And we also showed that we can combine it ideas based on minimal description length approach. In our work, we used some sort of non-parametric statistics like stability analysis, but we would like to extend our approaches, which are mostly structural, to involve more statistical reasoning in them. And I hope that our possible cooperation would help this. So, thank you for your attention. Now it's time for questions.
Yeah, thank you for this nice presentation. There is someone that would like to take say a comment or a question about what has been presented. I have a question. For example, you have show in this slide the case where a non-usual cluster, your model, fails regarding, for example, the BSCAN, and the case where they work well as k-means and also the BSCAN and so on. Could you please go to this?
Oh no, I should just. Here.
Yeah, probably is here. Yeah, this one. So my question is, for example, what you got with the k-means after you could eventually describe by hyperrectangle. Okay? And for you, what is the advantage to use the tools that you have used and then arrive to hyperrectangles regarding, for example, apply k-means first, and then after you can provide a description based on hyperrectangle also.
I think that it's, you see...
to complete the question.
I think that the answer is rather in the first slides, where you just suggest intervals of features which are quite understandable to humans. Because we propose constraints for each feature, not like sum of squares as the constraint on the distance, Euclidean distance, or other types of distances. So, but I would say that it would be nice to work to have these two views. So this approach can be built on top of approaches like k-means or k-nan for better interpretability.
Yes, but you obtain the cluster running simultaneously tools for interpretability. And the other option would be, I can apply just a numerical method, based method, and then after I use some tools to provide a
better explanation.
Explanation, for example.
Can be.
It could be also.
Yeah, it could be, yeah.
Okay. Well, thank you very much. Some other comments or
can you provide a bit more intuition about what is the bottleneck in your stability-based algorithm? Why is it kind of, as you mentioned, slow when you need to improve the performance of it?
Stability?
Your stability-based algorithm. Why? I mean, I wanted to get an intuition. What is the bottleneck there? What are the main steps that could be improved computationally speaking? At some point, I'm not sure if I understood correctly, but at the end you want to to obtain some sort of association rule based thing that explains it, right? The patterns you find.
You see, here we have. Sorry. Maybe this figure is more helpful. Here we have concepts which are stable with respect to some threshold. Do you see they are sparse? And to compute them, we need to go through non-stable until we reach some threshold. And that makes a problem because here they can be many non-stable objects, concepts in between. If it's that's why it'd be different from the frequent description mining, which is a famous task, and there was a famous algorithm called a priori. You see, these frequent descriptions are dense. You go, and every is frequent until you reach some threshold, and the rest would be frequent. Here, you need to find a tricky way to jump from one stable to another one. That's the bottleneck.
Yeah, I was just wondering if there is if there would be sorry, interesting to have any, maybe it's possible to have any approximation of it that would be easier to compute than the exact one.
Yeah, thank you. Yeah, that's really, we actually worked a lot on that. Actually, this is already an approximation because the stability research started from a definition, not delta, it's called delta set. Just the stability is the number of the relative number of subsets that would give the same description as the generalization of remaining subsets. And this is the number of subsets exponential, and compute so the denominator is exponent and the numerator is hard to compute. Actually, it's a sharp p-complete problem. And so we replace this definition with this, which is already an approximation of it. Stability of every pattern defined in this way is computed easily. But since you have potentially exponentially many patterns, you are not sure the next pattern will be above the threshold. So maybe we can find a similar interestingness measure which would allow us for faster computation.
Yeah, thank you.
Thank you.
Okay, I think that we can stop here. Thank you very much again for this nice presentation. And thank you very much to be present here.